This video covers how to make an open top box from 50-52 063-inch aluminum. The open corners of the box will be TIG welded. A spreadsheet is provided to figure all the dimensions for the flat layout, notches, and bends. Check out the links in the description for more of the details. Let's get started. Here's an end run look at the finished box we're going to make. The 50-52 aluminum alloy is easy to bend and weld if care is taken with setups. The spreadsheet calculates the flat layout dimensions from the 7 user input values. The link in the description will get you access to Libre Calc and Excel spreadsheet files. The spreadsheet does not use any macros but simply runs user input through formulas. A PDF drawing is also provided to help with specifying the flat layout, which is very simple. First, we need to blank out a piece of metal. Unfortunately, this is more difficult than it should be. The Enco 52-inch 16-gauge hydraulic shear can be used for blanking out sheet metal. It does have a back gauge, which includes some helpful features like fine adjustment thumb wheels, but the design suffers from some problems that make it tricky to set accurate cuts. With a bit of creativity, you can work around some of these problems. Today we're going to make a box or pan 4 1/4 by 4 1/4 by 2 inches. So that's our project for today. I put in those dimensions in the spreadsheet calculator. I don't know if you can see that there. 4 1/4, 4 1/4, 2 inches, and then we're working with an 063 bend radius, 063 50-52 aluminum, and a 0.138 inch bend allowance, which has worked out to be pretty accurate for other projects. The spreadsheet calculator spits out that I need a blank piece 8 24 thousandths by 8 24 thousandths. My shear back gauge is a little questionable. It's kind of hard to set it. So if you have precision parallels or any scrap pieces of sheet metal, you can create a gauge like I did here. And this gauge I've set using canty clamps. Probably see that there. Let's get that on there. So it says here about 8 26 25 thousandths. I don't know if you can kind of see that there. Certainly close enough for this project. So we'll use this to set the back gauge on the shear, and I'll show you that in a minute. The problem with this is you're limited with the amount of distance that you can cover. So if you need to make longer cuts, this isn't going to work. So you can cut sheet metal out and you can make longer pieces and you can create longer distances. I have a Fowler 24-inch caliper like this, which is actually pretty nice. It eats batteries even when it's off, so if you're not going to use it, if you have this model, take the battery out so the battery doesn't go dead. But this is pretty good, so you can measure anything from 0 to 24 inches with this. If you've got to go bigger than that, Starrett makes precision scales like this. And these scales, they're not cheap, but they're nice, laser engraved, 1/8 inch, 16th inch, 32nd inch, and 64th inch is the resolution. So there's 4 granularities on this scale. These scales, unfortunately, are not cheap, but they're accurate and they're nice to work with. So let's go over and blank out our sheet metal at 8 24 thousandths and take a look at what's going on with the back gauge. Here's my back gauge, and it suffers from a few little minor problems. It's got a thimble, thumb wheel type of arrangement, which is kind of nice. You lock this down, you loosen this a little bit, and then you can make fine adjustments forward and backward with this thumb wheel. Kind of looks like it's really a cool idea, and it is, but here's the problem. I don't know if you can see this or not, but there's slop in this bore that runs on this guide. See it here? This is really a lot of slop. So what happens is when you tighten the back gauge and you have a setting and you want to lock it in, when you tighten this, this lifts up and then actually changes the dimension that you want. It actually lessens it. So it's a little bit inconvenient to get this set, but you can play around with it. This kind of a gauge helps a little bit. You can actually put this in here and put that in between your shear. So I'm a little bit short here, so I can loosen this just a little bit, pull this back till it drops in. There we go. Got some slop in there. And then I can tighten this. That takes the slop out a little bit. There's just really no easy way with this setup to get this set really accurately. So you got to play around with it. And if this is too tight, then what happens is this gets pushed back and then you don't really get any type of adjustment on this. So it's a little bit of a pain. So you got to loosen this, then this drops down, then you can sort of tighten this up, leave a little slop in there, then tighten this back up and kind of hope for the best. So this is pretty close. And when you do this, you want to make sure that you measure right over the guides, because what will happen is as this guide, or as this side moves, it's going to cantilever this over here. It's going to swivel. So if you can set it here and you can set it over there, then the whole guide here generally is pretty parallel with the back. So that's kind of what's going on with this shear. I wish this was a little bit better, but it isn't, so you just have to deal with it. We went ahead and blanked out a piece of aluminum. I didn't show it because it's not that exciting, just a sheared piece of aluminum. But we set the back gauge up as best we could, so let's take a look at where we came out here. So this measures 8 27 thousandths, which actually is pretty good. Let's take a look at the other dimension. This one didn't come out so well. It's about 8 inches, so it's 24 thousandths short of where it should be. What's going to happen is when we bend this box, we're going to see that as an inaccuracy in the width. So what I'm expecting is one of our dimensions, 4 1/4 inches, are going to be pretty close. The other dimension is going to be about 24 thousandths or 25 thousandths short of where it should be. Maybe that's a problem, maybe it's not. Depends on what type of accuracy you're looking for. For me, it's a little frustrating, but it is what it is. But we'll go ahead and notch out these corners and do the bends and create the box. This is my notching machine. It used to be a hand crank job when I bought it many years ago, so you're a little sick and tired of pulling on the handle. It's a little tough on the shoulder too, because when the metal breaks through, it jolts the arm, and after a while it hurts your shoulder. So I went ahead and got a hydraulic pump with a valve, spool valve, and a hydraulic cylinder, and did the parts for all this and basically replaced the hand crank with a hydraulic mechanism, which works kind of nice. I got a foot pedal here, come down, come up, come down, come up, and then there are limit sensing cams on the side here with limit switches which control the valve so I don't travel further than what the machine is capable of. So this works out really well, and it saves your shoulder a little bit. Back on the sheet metal, the spreadsheet calls out a notch 1.944 inches by 1.944 inches for this project. So we set up our gauges and limits for that. So we'll go ahead and blank this out. There's 1, 2, 3, and 4. So there's our flat piece. Next we got to do the 4 bends and see how this comes out. Let's see how well we did on the notching. I've got my caliper set to 1.944 inches, which is the notch dimension. So we'll go ahead and just take a look here and see. It's a little bit out, it's a little big. I'm going to say maybe 5/10 thousandths of an inch big there, and probably about 10 thousandths there. So what's going to happen with that is it isn't going to affect the dimensions of the box or the dimension of the side. What it's going to affect is the opening of this open corner. That's what we're going to see. So it's going to be close enough. We should get a decent corner. I'm going to, later in the video, I'm going to weld these corners closed. So that should be kind of fun. So this piece is ready to bend into a pan. So let's go do that. Fire up the press brake. Get that started up. Cycle the machine. I've already set the back gauge to 1.944 inches, which matches this notch. So let's go ahead and bend this out. Okay, there's our box. We got open corners. We can hit this again. 1, 2, 3, 4. So there it is. Looks like it bent up pretty well. These corners are open as we expected. We can touch up these bends a little bit. You can see this metal is pretty flexible. So let's go ahead and measure this and see how close we got. Okay, let's see how well we did. We're looking for 2 inches here on the outside. This one's 3 thousandths short. I don't know if you can see that, 2 or 3 thousandths short. This one's just about dead nuts on, right at 2 inches. This one is 3/4 thousandths short. And this one's 1 thousandths short. So we did pretty well on the sides. We're expecting that one of these dimensions, because the flat piece was short, is also going to be short. We'll probably by about 25 thousandths. So we're looking for 4 1/4 by something about 25 thousandths less than 4 1/4. So let's see what we got going on here. So this is 2 thousandths shy. It's 4.248, which is pretty good considering how we did this. So this one here is going to be short, and this one measures 4.220. So if we add 25 thousandths to that, that would put us at 2.245, or about 5 thousandths short, which across 2 bends is pretty good. So we expected that. This kind of bent up, consistent with how our flat layout was. The inaccuracy there, again, is attributable to the shear and the flat dimensions not being as accurate as I would have liked to see them. But this box came out pretty well. Next thing is we got to weld these corners closed, so we'll tackle that challenge next. Here's my welding setup. I put in 2 pieces of scrap metal, 16th inch aluminum, and I simulated the open corner along here. Basically what I have is a right angle piece of extruded aluminum to hold this in proper form. It also takes the heat out of the metal because aluminum has a very watery puddle, and if you don't back it up with a heat sink, the metal just flows away and the corner opens up and you can't fill it, and it just turns into a mess. So I've got a guide here for my hand. Here's my TIG torch. So we can guide this along here this way to weld this corner closed. The purpose of this is to do a test weld to make sure that my gas flow, argon is good, my amperage is good, and all my welding parameters are good, so I don't ruin the box when I get to that part of the serious welding. So that's how I set it up here, and we'll see how this works out. The welder used for this project is a Lincoln Electric square wave TIG 175 as shown. You need a square wave to properly weld aluminum. This provides a cleaning action on the metal to remove oxides. Aluminum oxide has a much higher melting point than the base metal, making it a nuisance. The amperage is set to 110 amps for the 0.63-inch thick metal. Aluminum conducts heat away from the weld puddle quickly. Aluminum also produces a watery puddle, so you need to move the torch accordingly. Argon is the shielding gas used for aluminum. The pressure used here is around 27 pounds, which provides adequate gas flow through the gas lens and nozzle. Make sure there are no air currents present that will blow away the shielding gas. Air conditioners, fans, humidifiers, and heaters can cause problems. Welding in still air is best. A 3/32-inch tungsten electrode is used here with a 3/8-inch protrusion from the nozzle. A close-up of the 17 series torch, electrode, and nozzle are shown as an example. Use what works best for your specific welding conditions. I'll go ahead and do a test weld on scrap pieces of aluminum that match the alloy thickness and corner geometry. I don't have a welding lens for the camera, so I took a quick still shot of the arc. It's very bright. The test weld came out fine, so I replaced the scrap pieces with the box as shown and welded all 4 corners closed. Corners 1, 2, and 4 came out pretty well. You can see on corner 3, the puddle got away from me about halfway through the 2-inch weld. No harm done, as this is just cosmetic. You can dress welds with a file, but that removes metal and will weaken the joint. The choice depends on how nice the corners need to look. Okay, let's see how we did. If you have a set of precision V blocks, you can create a right angle reference here. So we welded 4 corners of this box. They were open. As I had mentioned, we used a piece of extruded aluminum right angle to kind of form these bends and also act as a heat sink while we were doing the welding, so the metal doesn't run away. But what happens with aluminum, since it has a high coefficient of thermal expansion, when the weld is finished, the metal shrinks and it creates distortion and stresses. So these edges here, you probably can't see, but they're pulled in slightly. So we'll just go in here, and this one's not too bad. You can probably see that one wiggle a little bit. So that's 1, 2. This one's pretty good. 3. This one's probably the worst. 4. So you could tweak these sides. You could go in here with a big adjustable wrench and probably pull these a little bit. Put a scale along here. You can kind of see what's going on there. The welds push it out, so it's kind of hard to really tell what's going on here, but I can see this edge. They're all kind of scalloped in a little bit, but this is to be expected. It's very hard to not avoid this. The next step for this would be to put this through an annealing process, and that's just not going to happen. There's no real need for it. So overall, this came out pretty well, and the dimensions are as we measured before and as we showed. So I'm pretty happy with it. So that's the box. Maybe we'll make a top for this.